Recording is rolling. Welcome to Thursday, May 4th. We're going to continue the final exam review where we left off yesterday. All right, so for video context here, we're in kind of wacky exam season. It's May, so my first few classes, I didn't even see you guys because I had I was proctoring an exam in this classroom. So all my classes are off a little bit, so this video may not align with your particular class. I'm using 7th period right now, if this is the video that goes up. And yesterday we left off on number 37, which is Newton's law of cooling question, right? So my other classes, if you're one of my morning classes, I'll get you guys caught up in time. Just be off sync a little bit. All right. I find this. Find something here. All right. So here, I know bell was ringing, guys were walking out the doors. I was finishing explaining this one. So let's look at this one real fast. This last one we did yesterday. Newton's law of cooling. Suppose you have a hot cup of water. It's emanating heat. It'll eventually reach the environmental temperature. So if I do temperature as a function of time, I can make the environmental temperature like a horizontal asymptote, right? And the initial temperature of the water might be like really hot. Okay, so it's going to follow this curve where described by Newton's law of cooling, Isaac Newton. This is one of the problems that he described mathematically. And the question has to do with the rate of change. Right? So do you guys see initially when it's really hot, there's a really steep slope? And then as time goes on, the slope gets shallow, 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 until when it's really close to room temperature, it changes really slowly. I guess that, right? By the way, that's also a calculus concept. So whenever you're talking about rates of change. Okay, that's the last one we did yesterday. 38. Planet Earth loses heat primarily by what? Radiation, convection, or conduction? What do you guys say? What's Earth surrounded by? The what of space? Vacuum. What's the only kind of heat transfer that can go through the vacuum of space? Radiation. Right? How does energy get to Earth from the sun? Radiation. How does Earth like pull off or like maintain some kind of balance so it doesn't just like greenhouse forever? Radiation. Right. These are the three main types of heat transfer, though, right? Radiation, convection, and conduction. At high altitudes, the boiling point of water. Ooh, so you go way up in the mountains where the air is really thin. Oh yeah.
So the answer to 38 is radiation?
Yeah, 38 radiation. 39 at high altitude. So we're going way up in the mountains where the air is really thin. Do you need to? Where would water boil? At 95 degrees Celsius or at 105 degrees Celsius? How about 95 degrees Celsius? Right. That's a lower temperature. Right. Let's take this to an extreme. Do you guys remember reduced pressure boiling? What happens if you put room temperature water in a vacuum? What does it start to do? Boil. So even at room temperature, water can boil, right? If you lower the pressure enough. When snow forms, the air around it becomes warmer. Interesting, right? Because, well, actually, it should make sense why, right? Because when snow forms, isn't that like maybe a cold liquid turning into a solid? Right? That's what snow is. It's like little ice crystals. Right? So when you go from liquid to solid, are you gaining or losing heat energy? You're losing heat energy, right? Now that's looking at the water itself that became snow. Does that heat energy just disappear from the universe? No. The first law of thermodynamics says heat energy, well, all energy in general, right, is conserved. So it goes somewhere. Hey, it goes to the surrounding air, which makes the surrounding air a little bit warmer, right? Let's see what answer choice aligns with that story I just told you. Changing from a vapor to a solid is a process that gives off energy. Hey, that's exactly what I just said. The first law of thermodynamics is a restatement of the conservation of energy, right? Energy is neither created nor destroyed. You know, it can take different forms. It can move into different systems or different objects, but the number of joules hanging around is always the same number of joules, right? First law of thermo. 42. The greater the difference in temperature between the input reservoir and the output reservoir of a heat engine, right? What happens to the efficiency? Okay, so here, I got one right here. I got it. You guys remember the Stirling engine? So right now it's all room temperature, but if you take say a hot cup of water and put it right underneath, doesn't it heat this up, which causes the air underneath to expand, right? And then it goes through the cycle and it like starts spinning, right? So we turn thermal energy into mechanical energy, but you need a temperature difference, like hot water versus room temperature air, right? You need a temperature difference. And if you want efficiency, well, I got to break out the equation. Okay. Do you guys remember efficiency? We're using Greek letter eta, looks like an N with an elongated tail. Right? So efficiency is equal to 1 minus the cold sink over the hot sink. Let me apply this a couple times. Okay. So let's run some examples of this. Okay. What if it's all the same temperature? What if it's room temperature, it's all the same temperature? Okay. What is this fraction right here equal to? 1, because the sinks are the same. So anything over itself is 1. Guys, what's 1 minus 1? 0. 0 efficiency. This thing's not going to spin at all if there's no temperature differential, right? What if you made the cold extremely cold, like close to absolute 0? You made the hot like really, really hot. What is this fraction approaching? 0. Like 0 divided by anything would be 0. What's 1 minus 0? 1. And as a percentage, you could call that 100%. So the efficiency could approach 100%, maybe never quite reach it, right? Now that's like ideal efficiency. Okay, so the question we're dealing with right now says the greater the difference in temperature between those two reservoirs, the greater the difference, what's happening to the efficiency?
It's increasing.
Increasing. It's getting more and more efficient. You see that? Right? All right, so guys, you can take whatever notes you want, of course, right? I always recommend that. The exam, remember I told you guys yesterday, I want to make this closed notes, but you guys are getting all the questions here, so you guys follow along, ask me any questions you have, study, I think you're gonna be all right. 2 identical blocks of iron, one at 10 degrees Celsius and one at 20 degrees Celsius, are put in contact. Pause right there. Let's get a picture going. So 2 identical blocks of iron. Okay. Let's call this guy 10 degrees Celsius and this guy 20 degrees Celsius. Right? Okay, so these 2 blocks. Okay. Now, guys, what would you naturally expect to happen if you leave them and come back an hour later? Yeah, they should both be about 15 degrees, right? That would make sense, right? They maintain all the energy, maybe it's insulated, same mass, same substance. Right. So let's continue with this question. Suppose the cooler block cools to 5 degrees Celsius and the warmer block warms to 25 degrees Celsius. Whoa. So you put these in contact, came back an hour later, and now this guy's down to 5 degrees Celsius. This one's up to 25 degrees Celsius. Hey, that's the opposite of what you said. Right? And that's the opposite of what you would have thought, because this would violate the what? First law or second law of thermo? The second law of thermo, right? Remember, the first law was the one that had to do with just quantity of energy is conserved, which actually this checks out, because if they're identical blocks, right, so same mass, same material, and one drops 5 degrees and the other picks up 5 degrees, that actually checks out according to the first law. There's nothing wrong with that by the first law of thermo, like energy is still conserved, right? But remember, the second law of thermo says something about the time order of processes, where if you put 10 and 20 degrees in contact, it should eventually reach an equilibrium of 15 degrees, given that you're moving forward in time, right? And entropy in the universe would increase, right? You guys remember that's the second law of thermo, right? And the second law of thermo would say that, well, it's not going to do, but the premise says here, the cold one gets colder and the hot one gets hotter, right? That would be the opposite, right? Now, guys, can you force this process to happen? Yeah, that's like what refrigeration is, right? But that's an energy intensive process. It's not just going to spontaneously happen, right? That's not. Right. Who's got questions so far? You guys all good? 44. Running a refrigerator with its door open in a hot room makes the room. Ooh, I just mentioned refrigeration, didn't I? So remember, if you start off with like, let's say like lukewarm air, like room temperature air, right? And then you want to make one side really cold, right? Well, where's the cold come from? Well, you're taking energy out, so the hot has to go somewhere. Usually you dump the hot into the room, or if it's air conditioning, you dump the hot out to the outside world, right? But remember, to do this, to make the cold colder and the hot hotter, that's reverse of what would happen spontaneously. So that's an energy intensive process, right? It's hard to do that. it requires an energy input. So if you go back and you mix the cold and the hot back together, overall, it's more what? Hot. Yeah, it's hotter, right? Because there's an energy input overall, right? So it's going to make the room warmer. Right? Makes the room warmer. Right? Is that? The ideal efficiency for a heat engine operating between 2050 Kelvin and 310 Kelvin is what percentage? And now it's really nice that they gave you Kelvin, because if they gave you Celsius, you'd have to convert to Kelvin anyway to get an absolute temperature. Right? So that you can plug it into this formula right here, this one right here, right? Well, here, let's do this. Right. So 1 minus, they said the cold sink was 310 Kelvin, and the hot sink was 2050 Kelvin, right? Just like that. Right, guys. Right. Now, when you guys get your exam, the numbers will probably be different, but it'll be the same story, right? You guys see this? So let's see what this is. What's 1 minus 310 Kelvin, or maybe I'll put that in parentheses just to be safe, right? 310 Kelvin divided by 2050 Kelvin, right? And I'm looking at 0.84878. I'll call that 8.849. About that, just round a little bit. Right? And as a percentage, you could call that what? Yeah, like 84.9%, or probably even better. Just let's do 2 digits. 85%. Right? Is that about 85% efficient? I'll say equals about right. 85% efficient, right? I guess okay. Ideal efficiency. Do I see that answer choice here? Yeah, 85%. Okay. You guys can solve that? Yeah. All right. Questions so far? All right, 46, standing waves. Okay, so I think we're moving on from thermo and heat transfer to waves and harmonic motion. Standing waves can be set up. Let me remind you guys what standing waves are. So say you pluck a guitar string. It goes wow, 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 wow. It doesn't have 2 nodes and one like antinode, right? Wow, 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 wow. Or do you guys remember I took a slinky and I attached it to the doorknob and stretched it across the room and was shaking it up and down like this, right? And then you can set up a standing wave this way too, where it's like wow, 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 wow. But now you have 3 nodes, right? And remember, if somebody walks up and touches this node right in the middle, does that affect the wow, 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 wow? No, it'll just, because that node doesn't move, so it doesn't actually. How many wavelengths did I just draw? 1. That is 1 full wavelength. You guys see 1 full S shape? So let's go back to the guitar string. How many wavelengths do you guys see right here? Half wavelength, 1 wavelength. What's that right there?
1.5.
1.5. What's that right there? 2. Right? Maybe you could shake a slinky up and down like that too, right? Now, those are all transverse waves. Remind you guys the other type of wave. If it's not transverse, it's probably what? Longitudinal. You guys remember taking those tuning forks, putting over the PVC pipes? Now the bottom was like water, right? You guys remember that water level? You guys remember that? So like closed it off, right? And then you strike the tuning fork, and sets up a standing wave. Well, it didn't set up a standing wave always. It was like you had to have the right position. So you take the PVC pipe, move it up and down the water, it goes like. Okay, so one place was like there could be a high pressure point here, and maybe it gets like low pressure as it goes out. And then you do approximately 3 times that, and there could be a high pressure point, maybe like 2/3 the way up. Okay. And it's longitudinal, but sometimes it's easier to see the transverse version. Okay, so okay, guys, okay. So that could be a standing wave also, just with longitudinal waves. Okay. All right, you guys remember all that? Let's go back to the questions. Standing waves can be set up by blowing across the top of a soda bottle. Ooh, I think that's kind of what I just drew right there. On strings and musical instruments. Oh, hey, let's pluck in a guitar string. And organ pipes. Oh, that also is kind of like blowing across the top of a bottle. It's a longitudinal wave. I think all those check out. Right? Those could all be some version of a standing wave. You think? Suppose a bug is jiggling up and down and swimming towards you at the same time. Compared to the frequency the bug is emitting waves, the frequency that the waves reaches you, let's check out. this bug. So here's a bug. Let's say the bug is in still water, like there's just a pond, and the bug is like moving to the right. So it's got some rightward velocity, the velocity, right? Hey, isn't the bug like catching up to the ripples that it's sending out, moving to the right? Right. So the bug is sending out ripples, bloop, 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 right? And it's catching up to the very ripples that it's sending out. So it looks something about like that. Right? Would that be right? Now maybe I just drew the crests of the waves. So if you get down like a level with the water, it would look like bloop, bloop, bloop. And if you look behind the bug, it goes bloop, bloop, bloop. Right? Is that true? Right. Let me ask you guys a different question that was not in your study guide, not in that packet. Right? What is the speed of the waves on the right compared to the speed of the waves on the left? The same. It's the same speed. See, like once the waves go out propagating into the water, it travels whatever speed goes through the water. Right? Now let's hit the target question. It's something about frequency. Guys, what is the frequency on the right compared to the left?
It's shorter.
It's a shorter wavelength, which means it's a
Smaller frequency.
higher frequency.
Oops.
Right? Shorter wavelength is higher frequency. You guys remember speed is equal to wavelength times frequency, right? So again, it's all the same speed waves. Right? Yeah, you're right that the wavelength is shorter, therefore the frequency is higher, right? Inverse relationship between those two. Okay, that was this question here. Compared to the frequency of the bug is emitting waves, the frequency of the waves reaching you is higher frequency. As the sound of a car's horn passes and recedes away from you, meow, meow, the pitch of the horn seems to what? Increase or decrease? Decrease, right? Oh, I forgot to mention this question and also the last question. There's a name for this effect. It's called the what effect?
Doppler.
Doppler. That's a Doppler effect right there, isn't it? Right? Replace the bug with a car and some more story. Meow. A child swings back and forth on the playground swing. If the child stands rather than sits, the time for a to and fro swing. All right, let's get a couple of swings going. Ooh, this sounds like a pendulum. Does that sound like a pendulum? Okay, pendulum swinging back and forth. You guys remember the time period to swing back and forth? It was like 2 pi times the square root of L over G. Right. Now we're comparing a couple of swings that have 2 pi is just a constant. Gravity field is going to be the same for both, right? So maybe I really care about the time period versus the length, right? So here the kid is sit down. So here's the kid, sit down, wee, right? Right? And then swing back and forth, swing, swing. Right? Versus what if we have maybe it's like the same swing set, or is it swing right next by? Right? I got a different kid, and this kid, he's standing up. Right? Hey, is the center mass of the first kid like probably right about there, and the effective length of this pendulum is like this long, versus the second kid, his center mass is right about there, and the effective length of the pendulum is only like this long. I'll call this maybe like L1 and L2, right? You guys see that the kid on the left has a long pendulum and the kid on the right has a short pendulum, right? So the kid on the left, maybe he's like swing, 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 right? The kid on the right, he's more like swing, 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 right? It's got to be a shorter time period to swing back and forth. But I should say back and forth is one time period, right? It's like, that's one time period. That's one time period, right? And here, we're looking for the relationship between these two, right? So if you have a shorter length, you also have a shorter time period. I guess that's what's going to answer that question. Suppose a simple pendulum is suspended in an elevator. Ooh, when the elevator is accelerating upward. Oh, right. So let's get an elevator going. Then we do some physics like we just did. I got a pendulum swinging in an elevator. Okay. How much time does it take to swing back and forth? Oh, that's going to be 2 pi times the square root of the length of the pendulum divided by the gravity field of the planet. Okay. Length of the pendulum is whatever it is. There's some mass here. Okay, put it right. Doesn't show up in the equation anyway. Right. Now, if the elevator is either not moving or it's moving at constant velocity up or down, then just this equation, that's the entire story. But if it's accelerating upward acceleration, ooh, if you're standing inside this elevator, do you feel really light or really heavy? Heavy. You feel really heavy. Like somebody just turned the gravity up, right? Feel real heavy? Should I do this? Plus A right down here? Right? Maybe I could prove that, but that's what it would be, right? So if you're turning the gravity up, then what's happening to the time period?
It's decreasing.
Decreasing, right? You guys see sort of like an inverse relationship between these two? If the gravity field's getting bigger, bigger, well, apparent gravity field, right? The time periods get less and less, right? So when the elevator was in equilibrium, maybe the pendulum was doing this. Swing, swing, swing. When it's accelerating upward, maybe it's more like swing, 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 right? Shorter time period. A sound wave that has a higher frequency has a wavelength that is, say, speed of a wave is equal to wavelength times frequency, right? Now, the sound wave, say like about 340 meters per second through air, right? So if you have a higher frequency, turn up the frequency, what had to happen to the wavelength? How do you get shorter, right? So maybe we were looking at this type wave compared to this type wave, right? This one has a long wavelength and a low frequency. This one has a short wavelength and a high frequency. Right, you guys see that inverse relationship? Or tell you, what if you want numbers? Let's have a wave go 100 meters per second just to get some numbers on the board. Let's say 10 meters long, and it cycles with the frequency of 10 hertz. Right? Hertz is like 1/seconds. Meters. Okay. What if you had a different wave that was like, well, it was like the same type wave, right? But you made the wavelength shorter, like 5 meters. Now, do you guys see the frequency is going to be like 20 hertz to make it go at the same speed, right? Because whatever type of wave you're talking about, whatever speed it is for that medium, right? Like here, if I talk in a low pitch voice, the sound's still going at speed of sound. If I talk in a high pitch voice, it's still the same speed, just different frequencies at different wavelengths. You guys get that? Yeah. Oops. Yeah. Yeah, a higher frequency is a shorter wavelength. Yeah, there you go. A leaf on a pond oscillates up and down 2 cycles per second as a water wave passes. What is the wave's frequency? Ooh, 2 cycles per second. Guys, that describes a what? Frequency. Isn't that just the answer right there? Right? 2 cycles per second is called 2 hertz. 2 hertz. Okay. So let's get a leaf going here. So I got a leaf, right? And it's on this water. It's going like bob, 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 right? Okay. So it's like bob, 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 bob. Isn't that like 2 cycles per second? Right? Guys, what's the relationship between frequency and time period? Frequency is 1 over the time period, or if you like, you could say the time period is 1 over the frequency. So in this case, if you're doing like bob, 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 where it's like 2 cycles per second, that's like 2 hertz. What's the time period between bobs?
1 second.
1 divided by 2 hertz is?
Oh, 1/2.
Well, half a second. There's like a half a second between bobs, right? See this leaf like bobbing up and down with those water waves, right? Okay, guess that. Radio waves travel at the speed of light, 300,000 kilometers per second. The wavelength of a radio wave at 200 megahertz is, okay. So we've got speed is equal to wavelength times frequency. Except here we are talking about the speed of light, so it is a special speed. Maybe I'll change this V to a C. But it's still the same idea, wavelength times frequency, right? It's just for the special speed. Okay. Now, we're going to have to do a little bit of conversion here with the prefixes. Guys, 300,000 kilometers per second. How many meters per second is that? 3 times 10 to the 8 meters per second. Or we're talking about the speed of light, speed of radio waves. It's all the same speed of electromagnetic waves. So the question is, what's the wavelength? Solving for the wavelength. And the frequency is at 200 megahertz. So that's 200. Now, mega, guys, mega is 10 to the what? 6, right? Hertz is like 1/second, cycles per second. Right, would that be true? Right, you guys, yeah. So if I'm solving for a wavelength, can I take 3 times 10 to the 8 meters per second and divide by this 200 megahertz? So it's like 3, here, I'll write it out. 10 to the 8, that's 8 zeros. Meters per second. All divided by this 200, and then times a million hertz. That's 6 more zeros. And hertz is like 1/seconds. Meters. Zip, 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 zip. Hey, what's 3/2? 1.5, and the unit is meters. To describe a wavelength. There you go, 1.5 meters. Okay. Now, of course, when you guys get the exam, your numbers will probably be different, but it'll be the same story. Can you guys do little conversions and just divide? You guys can figure that out? Okay. That's not too bad, right? It's good. Okay, here we go. Sound waves cannot travel in a what? A vacuum, right? Vacuum, right? Remember, sound needs a medium to go through. Right? Does light need a medium? No, light can just travel through the vacuum of space. That's that whole Michelson-Morley we were talking about with the Kirchhoff relativity. Noise canceling headphones are an example of what? There you go, destructive interference. Destructive interference. Just that. Okay. So let me remind you guys what that was. Okay. Suppose you have like a taut string. Oh, whoops. Oh, it's supposed to be a start over. Line over. Right. So you have a string, right? And you start sending pulses through it, right? Like pulse, pulse, right? And say I got a pulse like this traveling to the right, and I got a pulse like this traveling to the left, right? Right. When they cross over each other, what does it look like? It's totally canceled out like a flat string, right? And of course, that only lasts for an instant, and then they'll just like keep on passing through each other and keep on moving. You guys remember that? You guys remember that video demo? Right, right. But while they're crossed, like crest to trough, yeah, it goes back to flat string. That's called destructive interference. Right? Now, I just drew transverse waves, but if you replace those with longitudinal waves, like sound waves, right? Now you've got noise canceling headphones, right? So noise canceling headphones will take the ambient sound from the world, right? Oh, invert it, mix it with that sound, and cancel it out. So it's an active process. The speed of sound and dry air at 20 degrees Celsius is 340 meters per second. You guys have used that number 3 times, 340 meters per second. How far away is a jet plane when you notice a 2-second delay between seeing the plane and hearing it, right? Or if you like, you could change out the plane with, how about a bolt of lightning, and then you hear the thunder 2 seconds later, right? So it's gonna be the same math. How far away is the lightning?
680 meters.
680 meters. There you go. Nice. Okay. You write it out. So speed is that's up again. Distance is equal to speed times time. That's what we're doing. Distance is speed times time. That's one of the first things we ever did in this class. In fact, you guys knew this before you ever walked in this class, and I can prove it to you. If you're driving 60 miles an hour and you do that for 3 hours, how far have you driven? 180 miles. You guys do that before you ever saw this classroom, right? Okay. And so now we're going to take 340 meters per second for the speed of sound. We're going to say we notice a 2-second delay in between seeing the lightning and hearing the thunder. Exactly. 680 meters away. You guys see that? Which of the following are fundamentally different from the others? Right? So we've got a list of different kinds of waves, and 4 of these are the same category of wave, and one of them is like totally different phenomena. We've got X-rays, radio waves, gamma rays, sound waves, light waves. Which one is not like the others? Sound, exactly, sound. Because the other 4 are all what kind of wave?
Electromagnetic.
Electromagnetic, right? They all, you can say electromagnetic, transverse, travel at the speed of light. That would all be true, right? But sound waves, right? Sound waves are longitudinal pressure waves that need a medium, travel much slower than the speed of light. Right? So totally. The main difference between a radio wave and a light wave is, guys, do radio waves and light waves both travel at the speed of light? Yep. The speed of light is really the speed of all electromagnetic waves or anything massless, really. Right? So do they have different speeds? Do they have different wavelengths? Bing. Here's a radio wave. It might have a crest to crest wavelength of, I'll call it lambda radio. Of, oh, I don't know, let's call it like 3 meters, for example. Right? That doesn't have to be, but a lot of the broadcasts on FM radio is like about that long, right? Here's a light wave. The wavelength, and that's not even the scale because the wavelength is like, or call it like 600 nanometers. I think it's somewhere in there. It's like nanometers, right? But do these waves travel at the same speed? Yep, 3 times 10 to the 8 meters per second. Different wavelengths, different frequencies. Right, so wavelength in this case, right? Main difference. The main difference between a radio wave and a sound wave, a radio wave and a sound wave. Ooh, a radio waves, electromagnetic spectrum. Sound waves, there's your pressure wave. That's how you're hearing me talk right now. Okay. Is it basic nature?
Yeah.
Yeah, that's it, right? Maybe also wavelength, energy, amplitude, frequency, but yeah, definitely basic nature. We're talking about different categories of things. Compared to the speed in air, the speed of light in water is what?
Same.
Hold on, careful. Here, how does this refraction lens work? Because when light goes through the glass, it has to slow down, right? Right? Is that true? Right. So do you guys remember Snell's law? Yeah, it's slower through water and glass than it is through air, right? Like the speed of light through a vacuum is 3 times 10 to the 8 meters per second. Through air, it's almost that. You could kind of call it that. Right? But through glass and water, ooh, now it's significantly slower, right? You guys remember like index of refraction of like 1.5? Right. Tell you take the speed of light, divide by 1.5. They'll tell you the speed of light inside the glass. Okay. Okay, speed of light in water is slower. Okay. An electron vibrates up and down 1,000 times each second. It generates an electromagnetic wave having a what? 1,000 times per second. That's called 1,000 hertz. 1,000 hertz, which is a frequency. Right? 1,000 cycles per second. That's a frequency of 1,000 hertz. Okay. Guys good? Two polarizing filters held at right angles to each other. The amount of light transmitted. Right here, we'll do this one right here. I got a polarizing filter vertical, polarizing filter vertical. Vertical, cross them over each other. Most of the light gets through. I guess it. Right. But what if I take this one on the right here? 90 degrees. Now I got vertical versus horizontal. What's gonna happen when I cross these over each other? No light gets through. Look at that. It's pitch black, right? Okay, see that? Polarizing filters. Colors seen on a TV or computer screen or your phone screen, that results from color what? Addition, right? Like for example, if your phone screen is black, then what lights are lit up?
None.
Yeah, none at all. Right? What if your phone screen is white? All the colors RG and B, which is one of the colors coming up, by the way. Yeah, let's skip a question here. The colored dots on a TV screen are
red, green, and blue.
Red, green, and blue. There you go. The RGB standard, red, green, and blue. Right. Hey, how do you make yellow? How does yellow show up on your phone screen?
Red and green.
Yeah, red and green. So there's like, if you go down microscopic, yeah, flash on the red and the green, it's gonna look like yellow if you back up. Right. Oh yeah. 62, yeah. The polarizing filters. Yeah. It's 0, right? So see if it's like vertical, the light gets through. If it's vertical, horizontal, 0 light gets through if they're at 90 degrees. Yeah, there you go. All right. Yeah, so your phone screens, computer screens only have 3 bulbs in them, right? Red, green, and blue. The one I skipped here, 64. Colors seen on a photograph result from color what?
Subtraction.
Subtraction. So where's your phone screen? I think I mentioned too. If all the lights are, guys, if all the lights are going on your phone screen, what color does it make? White, right? But okay, now let's switch over to back to photographs. How about your color printer, guys? What are the 3 colors you have in your color printer?
Magenta, cyan, and yellow,
There you go, magenta, cyan, and yellow.
and also black. They have an extra.
Well, yeah, okay, you're right. Yeah,
why-
that,
that's
just
why
a
it's
regular
format-
black.
That's why when you
cartridge
format
tape.
something for printing,
Okay.
it's
Uh,
CMYK.
Right, yeah, okay for black. But suppose you run out of black ink.
Well, you can just substitute it using cyan, magenta.
Exactly, right. You get all 3 of those going, the cyan, the magenta, and the yellow at the same time. Now you're back to black ink. Right. That's right. Right. And that's color subtraction, because the more ink that you add, it subtracts more and more color, right? Which is the opposite of what's going on your phone screen. Your phone screen, the more bulbs you have, the more it gets white light. On a printer, the more colors you put in, the more it gets like black ink. All right. The law of reflection says, law of reflection. Draw this one out. If I got a mirror surface and I'm looking at this normal line right here. Right, it's that normal line, right? Okay. And let's break out the pink ink. Let's say I got a light ray bouncing off. For boing. Like that. I guess that light ray, boing. Right. Let's call this angle of incidence. And this right here, I'll call the angle of reflection. Right. Suppose the angle of incidence, I'm just gonna make something up. Let's say this is like 32 degrees. What is this angle of reflection right here? 32 degrees. Right. Are those always the same? Yep, that's what the law of reflection says. Okay. Now, what if your mirrored surface is like a curvy, like a funhouse mirror? Ooh, I got like a curvy mirror here. Got plane on this side, curvy on this side. Okay. Now, point for point, that would still be true, and then that effect is what we'll call work. Yeah. But the angle of reflection equals the angle of incidence. That's what we're looking for. Those 2 angles are always the same. That's the law of reflection. Okay, the law of reflection says that the angle of reflection from a mirror equals the angle of incidence. Okay. A person standing waist deep in a swimming pool appears to have short legs because of what?
Refraction.
Refraction. There you go. Refraction. Okay. Where's my? Here's a different use of refraction right here. Right. Guys remember this? Right. Light bends when it slows down through either like glass or water. The shortest plane mirror that you can see your entire image is what compared to your height?
Half of it?
It is half your height. It is half your height. I want to remind you guys why that is. So let's get a floor going. Okay. And let's have a guy stand here. Oh, stick figure guy. Right. And let's say he's standing in front of a dresser mirror that is also his height. Right. It doesn't have to be, but I'll show you guys why. Right. Do you think he's going to see a reflection of himself that's going to look approximately like here, about something like that? He sees his reflection, right? Opposite side, same size because it's a plane mirror. Okay, now let's follow a couple of rays of light. Again, I'm trying to prove to you guys that you don't actually need the entire mirror. You only need half this height. Right? So let's give him an eyeball right here. Right, he's looking at his reflection over here. Let's look back at him. And from his eye, he can see the top of his head, and that came from a boing, light ray that came this way, right? Which is almost horizontal. Right? Not exactly horizontal, but pretty close. It's pretty close to the top of his head. And then he looks down and he sees his feet. Boing. Right? Is that? Right. And if he's looking at the top of his head, the bottom of his feet, doesn't he see his entire reflection just in this bit of the mirror right here? Right? You guys remember that? Right. Let's make some measurements. I got a measuring tool right here. So I just sketched this freehand, but we'll see how close this is. All right. So my big mirror is it's almost 6 centimeters tall. Right? Is that? How about this little bit right here? Ooh, almost 3 centimeters tall. 3 centimeters compared to 6 centimeters. Look at there. Right, A rainbow nicely illustrates an example of light. I don't know if we actually covered this in class, but maybe you know,
Refraction
refraction and also
and internal reflection?
and internal reflection, both A and B. Here,
That was just the first one.
I will draw this out for you guys. You can see a rainbow here. So, okay, when you're looking at a rainbow, where is the sun compared to where you're looking? It's always behind you, right? So let's say you're looking out this way. Okay, I say, hey, there's a rainbow. Try to draw a little 3D here. Okay, got some rainbow bands. Okay, so that could be like a rainbow band. Okay, so the sun is actually like back here behind you. Okay? And wherever you're looking at where the rainbow is, that air has a lot of what in it? Water droplets, a lot of humidity, a lot of water droplets. Okay? So I'm going to draw those water droplets. I'll exaggerate them, make them real big. Okay, let's say we got some nice big water droplets going on, right? Just for visual. Right. So let's follow a ray of light and see what's going to happen. So we got light from the sun. Okay, it's this droplet here. It refracts, then it reflects internally off the back, and then it refracts back out, right? It's going to do like that, like I said. And does every wavelength of light refract a little bit differently? Yeah, it's a term for that. You can call that chromatic aberration, right? And that's what creates that rainbow effect. Now we got a rainbow. I got a rainbow. You guys good? Questions there? All right, so yeah, there's refraction, internal reflection, refraction, and boom, now you see it. Oops. Number 70. Chromatic aberration occurs because different colored light rays. Are you going to say refracted? Oh, let me zoom in so you guys see this. Right. Refracted different angles passing through a lens. Right. Chromatic aberration. Right. So kind of what I was just talking about, sort of. Right. It's involved with the rainbow. Right. That's what makes a rainbow work. Let me mention another example where this came up earlier this semester. Right, is we were talking about telescopes. You guys remember to take a couple of these lenses, refracting lenses, you make a telescope, aim this up at the sky, say, hey, there's Jupiter. You guys remember that? Right? But one of the problems they had with these refracting lenses is this right here, this chromatic aberration. So like back in like 1600, you could see Jupiter, but you couldn't see a real crisp image of Jupiter. It was a little bit fuzzy, right? Okay. And what was the solution to that? It was an Isaac Newton invention. Instead of using a refracting lens, you use a reflecting mirror. You give it a little bit of concavity, just like this one, a little bit of concavity, right? Actually, modern day telescopes, like the high end ones, like the Hubble, for example, right? Based on that technology, that Isaac Newton reflecting telescope, because the reflecting telescope doesn't have this chromatic aberration. A magnifying glass underwater will magnify. Okay, now this has to do with Snell's law. We're going to compare indices of refraction. So a perfect vacuum is exactly 1. Air is pretty close to 1. We'll just call it 1, 2. Right, so air index of refraction is 1. This glass index of refraction might be like 1.5, right? And you need a difference in indices of refraction to get this, to get refraction, right? So to get this magnification. Right? Water has an index of refraction of like 1.3 something. Right? So this glass compared to air is like 1.5 versus 1.3. Oops, back up. This glass compared to air is like 1.5 compared to 1.0. If you dunk this underwater, now it's like 1.5 compared to 1.3. Is there going to be as much of a change in speed?
No.
There isn't. So is there going to be as much refraction, as much magnification?
No.
No, right? Right. So you guys remember if you're like magnifying the bottom of the swimming pool? Yeah, right? Doesn't magnify as much. The fundamental force underlying all chemical reaction. Hey, this is the last one you guys did in your quantum journals. You guys turned this in, by the way. Right? Quantum journal. Four fundamental forces. One of them we talked about was the gravitational force. There was, I was calling it electromagnetic force. Here it just says electrical, but they're talking about the same thing, right? And then there were like 2 nuclear forces, right? Guys, which one's involved in chemistry? Yeah, electrical. You could say electrical, electromagnetic. Same idea, right? Because it's electrons interacting with electrons, right? Like valence electrons. Is that true? Guys good? To be safe in the case of a lightning strike, it's best to be framed, inside a building framed with wood or steel.
Steel.
Let's go with steel, right, because that's a conductive material, path of least resistance. Lightning wants to go through the frame and not through you. All right, that's gonna be our pause point right there.